Hi, I'm Pete Collins. I'm professor in the Department of Materials Science and Engineering. Our research group works on advanced alloys for aerospace and defense applications. We specialize in titanium alloys. The group has three main activities: materials characterization, materials processing, especially 3D printing and additive manufacturing, and using models to go ahead and predict the properties and performance of materials in the most demanding of applications. Undergraduate students are an essential part of our team and often are involved in some of the most innovative activities that we have in our research group.
Hello, my name is Maddie Harrington. I'm an undergraduate researcher for Dr. Collins' group. I'm working mostly with characterizing additively manufactured titanium alloys. This is an example of one of the samples we have, and this is an alloy called 5553. So this is a cross-section of titanium, and what we do is we stick this into the SEM and look at the microstructure up close to understand its properties and behavior. So after we prepare our sample, get it all cleaned and polished for looking at under the microscope, we put it into the SEM, and what we're looking for are different phases within the microstructure. And we're just looking at kind of the shapes of these features, the actual volume fraction and distribution of these features, and we're also looking at certain defects within the build as well. We can then put the images into this state-of-the-art image analysis software called MyPar, and what this does is it allows us to input these images, apply a deep learning model that we've trained to select certain features of interest. For instance, we are interested in these dark grain boundary alpha lats, so we can train these models within MyPar to select those features. And then after we've selected those features, we can look at all of these highlighted regions and do quantification based on the pixel size of these features.
Hi, my name is Kelsey McInturf. I'm another undergraduate researcher in Dr. Peter Collins' group. My focus in the group is on data science and visualizations. Now that we have hundreds of data points from Maddie's work in MyPar, these data points are representing very different materials properties and engineering performance. We need to understand the complex physics that dictates these relationships. In order to do so, we are able to use sophisticated machine learning to help us understand these physics and statistical methods to say how good our models actually are. With this group, I'm able to learn content that isn't necessarily taught in the classroom, but by learning and practicing the data visualization, regression, and analysis tools that I use each week, I can see how I'm helping move this problem forward. Some of the tools that I use to accomplish this are coding languages like Python and R, and specific packages like Keras and TensorFlow, which allow me to build neural networks to predict the materials properties of titanium alloys based on the physical characteristics Maddie saw in her image processing. These trend lines, and more importantly, the outliers, give us insight into how these alloys perform. Through undergraduate research, I'm able to combine my interests in material science and data science and use these skills to solve real problems. The tools I've been able to develop in my research are microscopy and machine learning techniques, which is a unique opportunity within our department. The best part about working in this group is that even as undergraduates, we are given creative and executive control over our own projects, which has been a really great way to explore our strengths.
I decided to switch to materials engineering is because I was looking for more hands-on work with what I was doing. By joining this research project, I've been able to develop crucial operational skills for materials characterization, metallurgy, basically by doing sample preparation, spending a lot of time on the scanning electron microscope, doing microscopy, and overall just getting comfortable working in the materials lab.
And the hands-on experience that we're getting is really great for our future jobs. Specifically, my experience solving real materials problems with data science techniques helped me stand apart in my job search. After graduation, I'm lucky enough to be working with Boeing, where I was specifically selected for my experience working with data.
Right, so all the skills we're developing are directly applicable into our post-graduation jobs. So I'll be working as a test engineer at the Sierra Nevada Corporation, and they were specifically interested in some of the hands-on work I was doing, as well as some of the problem solving on many of the projects. So we've worked on a wide array of projects within this research group, specifically with some of the things Dr. Collins talked about, the materials characterization. So we've collected hundreds of images using the scanning electron microscope, and after that, we just stick these into the image analysis software to quantify what we're seeing visually. So all of this is to say that we're able to provide evidence, through their interview processes and for our future employers that, the work we're doing is important, we're passionate about it, and we're able to show that we can work with other people to problem solve creatively when we hit obstacles in our projects.
Yeah, ultimately the work we're doing allows us to be part of innovative and exciting projects regarding high-performance materials and advanced manufacturing for aerospace and defense applications. The knowledge and skills we've gained are directly applicable to going on to work in those industries.